All right, today is Thursday, June 25. So in our previous video class, we talked about the definition of the Laplace transform. We made a brief introduction to this chapter, and we did a few examples about how to use the definition of the Laplace transform. Today, we will talk about inverse transforms and transforms of derivatives. So in this section, we take a few small steps into an investigation of how the Laplace transform can be used to solve certain types of equations for an unknown function. We begin the discussion with the concept of the inverse Laplace transform, or more precisely, the inverse of a Laplace transform, capital F of S. So first, we talk about the inverse transforms. Okay, now, yesterday, we learned how to transform a function, right? Using that Laplace transform. And what we did here, if you remember, we transformed the function f of t is equal to 1, or f of t is equal to t, and f of t is equal to sine of at, and f of t equals cosine of at, and sinh of at, or cos of at, and also e to the power at. All right. And also, actually, there is a converse operation, right? By actually using the inverse of Laplace transform, if we know it is transformation, right? And also we can actually get back our original function, that f of t. As you see here, we know that Laplace transform of 1 is equal to 1 over s, right? And how about if we apply this, the inverse of the Laplace to both sides, right? Here we will get inverse, Laplace inverse of 1 over s, that's equal to 1. And here, this is our function, that is f of t, right? And for example, Laplace transform of t, that's equal to 1 over s squared, right? And by using that inverse operation of Laplace, we can actually find that original function at t. So in Laplace inverse, or inverse of Laplace, 1 over s squared, that gives us t. Okay, it is like inverse function. And also here we have Laplace transform of e to the power negative 3t, for example. That's equal to 1 over s plus 3, right? And it is inverse. If you just apply here, what I'm doing here is like inverse of Laplace. And here we have L, right? Here we have e to the power minus 3t. That's equal to inverse of Laplace, 1 over s plus 3, right? And here's like matrix inverse of each other, right? First, take the Laplace and its inverse. They are gone. Only this thing is left here. Is the power negative 3t. And on the right hand side, we have this. Okay. Now, by using this one, soon, actually, we will take some small steps to solve linear differential equations with constant coefficients using this Laplace transform. Okay. These things we have already done yesterday, right? And also these are some inverse transforms. Inverse transform of 1 over s, that's equal to 1, right? And we know that Laplace transform of t to the power n is equal to n factorial over s to the power n plus 1. So inverse transform of this function is equal to this. That means that yesterday we learned how to transform this function, right, to another function. Here we have f of t, and here we are transforming this into f of s using Laplace transform, right? But now we're talking about converse, right? That inverse. That is, we know this function, how can I get this function? Or what functions in Laplace transform gives us f of s. If f is given, the question is, how can I get this function? To do this one, we are just using here the inverse operation here. Okay, that's it. So this is what we did yesterday. That is inverse Laplace of 1 over s minus a. That's equal to e to the power at, right? And the sine of kt, we know that it is Laplace transform equals k over s squared plus k squared. So it is inverse is, what is it? Inverse of k over s squared plus k squared. That's equal to sine of kt. Then here we have cosine. Here we have sinh of kt. Here we have cos of kt. Okay. And of course, we are going to generate a lot of formulas, even for Laplace transform. There's a huge book, but we are not going to learn everything because in the future, if you get the idea, for example, you are going to use it maybe in electrical engineering or in computer science or civil engineering, depending on your field, you may make use of it. Okay. Now let's just see some examples here. First one, find the Laplace inverse Laplace of this function. That means that in question A, this capital F that is given, that is 1 over s to the power 5, right? Here we know that Laplace transform of some function f of t, that is equal to 1 over s to the power 5, which is f of s, right? So we need to find what is f of t, this f of t. From here, applying the inverse transform f of t is equal to inverse Laplace of 1 over s to the power 5. And we know that Laplace transform has linearity property, right? And also this inverse has linearity property. That means that I can just multiply by constant number or bring this inside or take this outside, doesn't matter. And using the first formula here, this one, here we have n factorial, n plus 1. Here we have t to the power n, right? So here we have already 5. So I need here, what I need here? Here, this one is n plus 1, right? So I need here n factorial. That means that if I just multiply and divide by 4 factorial, so I can just write it as 1 over 4 factorial times inverse Laplace of, here we have 4 factorial over s to the power 4 plus 1, right? Here we have n factorial over s to the power n plus 1. What is it? That is equal to, we know that t to the power 4. Laplace transform of t to the power 4 gives us this, right? So that's equal to 4 factorial is 1 times 2 times 3 times 4. That's equal to 1 over 24 times, how about this thing? That's equal to t to the power 4, or simply t to the power 4 over 24. Okay. B, how about this thing? See here, it looks like something like this, right? Here we have s squared plus k, and if we have something constant, right? Here we have a squared, if we have a, that is Laplace transform of sine of at. So I can just bring this into that form. So as you see here, it looks like this thing, right? Here we have k over k squared. How can I do this? Here we have, let's say that a function is g of t is equal to, and the Laplace, inverse Laplace of 1 over s squared plus, I can write this 7 as square root of 7 squared, right? And to bring this into that form, I need to multiply, we need to have here square root of 7. So I just multiply and divide by square root of 7, just doing some simple algebraic manipulation. And here we have square root of 7 over s squared plus square root of 7 squared. Right? So what we have here, if we have k here, right, s squared plus k squared, right? And we know that that is Laplace transform of, what is this, sine of square root of 7 times t. So this thing is equal to 1 over square root of 7 times sine of square root of 7 t. Okay. Some examples. So also, what is this? Laplace inverse or inverse of Laplace transform is a linear transform. All right. It's similar to Laplace transform. That means that inverse Laplace transform of alpha times f plus beta times g is the same as the linear combination of their inverses. That means that inverse of linear combination of two functions is the same as the linear combination of the inverses. Right? That means if we have constant here, we can just take this out, constant, and also we can just separate them. Okay. So using that property, how do we evaluate this Laplace inverse or inverse? What is it? Laplace inverse of this function. That means that here f of s is given, right? Here we have f of s that's equal to negative 2s plus 6 over s squared plus 4, right? Or if I decompose this fraction, here we have s squared 4. I can just write it as negative 2 times, here we have s over s squared plus 2 squared plus, here we have 6, right? And here we have 4. I can write it as 3 times 2 over s squared plus 2 squared. Here we have alpha, right? Let me just denote this alpha. And this one is capital F of S. Here we have beta. And here we have capital G of S. So these things are Laplace transform of some function. Let's say this one is f of t. F of t is Laplace transform. This one is g of t is Laplace transform, right? So I need to get the original function, right? Let's say that is f of t. What is that? That is inverse Laplace of f of s, right? What is our f is given by this. And using the linearity property of Laplace inverse of Laplace transformation here, Laplace transform, so I can just write it as negative 2 times inverse of this Laplace s over s squared plus 2 squared, right? Plus here we have 3 because it's a constant. I can just take this out. Here we have inverse 2 over s squared plus 2 squared, which is equal to negative 2. And now you're familiar with this, right? Here, s over s squared plus 2 squared. It is the Laplace transform of cosine of 2t, because when we have s here, and something squared, right? That is Laplace transform of cosine of 2t. Okay, plus 3. And how about this thing? It is the Laplace transform of sine of 2t, right? So that is equal to sine of 2t. Okay, so this function is represented by this function in another space, right? Actually, if I do Laplace transform on this function, we get this thing. And its inverse gives us this function. It's like about the function and it is inverse, right? Okay. Another function. Now you got the idea. Here we are given f of s. F of s is a huge thing, right? It's a huge fraction, algebraic fraction. To deal with this one, we have to decompose this, okay? And also you should actually, if you remember, you learned, we studied this in pre-calculus. If you're given any rational function means it is the function that is obtained by dividing a polynomial function by another polynomial function. Simply the quotient of two polynomial functions. Rational function is, here we have p of x over q of x. Of course, this one is non-zero in the domain. Okay, this one is polynomial function. This one is also polynomial function. So we call this rational function. So here we have rational function, right? Because this one is polynomial function of degree 2. How about this thing? It is a polynomial function of degree 3. Because if you expand this, we will get here s cubed and plus something, right? The highest degree of the unknown here is 3. And we have to decompose this. How can I do this? Since actually all the factors are linear here, right? If you remember first, I should write this in this form. Because after we factorize the denominator, and all the factors of the denominator are linear functions, right? And we are assuming that I can decompose this in this form. Okay, So that is a over s minus 1, the first thing, b over s minus 2, plus c over s plus 4. So actually here we are assuming that this thing is identity. For every value of s, left-hand side is equal to right-hand side. Since it is an identity, right, by just substituting some suitable value for s, I can determine the values of capital A and capital B and capital C, right? The first one, for example, if I bring it into the same common denominator of the right-hand side, what we have here? A times s minus 2, s plus 4, s minus s plus 4, plus b times s minus 1, s plus 4. Well, you know how to bring into the common denominator. C times s minus 1, s minus 2, right? S minus 1, s minus 2. So now, how can I, for example, get the value of A? Since this is identity, that's not an equation for every value of s, left-hand side equals right-hand side. For example, if s equals 1, right? If s equals 1, this will disappear because it becomes 0. And also this will disappear, only this thing's left, right? And I can get the value of A. So the first thing is, if s equals 1, right? Substitute here on the left-hand side, I have 5, not 5, 16. It is 1 plus 6, it is 7, 7 plus 9, it is 16. How about here? 1 minus 2, negative 1, 1 plus 4, 5, negative 1 times 5 is equal to negative 5. And if you divide both sides by negative 5, I get the value of A, capital A, right? Now, second thing, I need to determine the value of capital B, right? Here, as you see here, we don't have 2. So if s equals 2, this will disappear, and also this will disappear because of this factor, right? And only b left. In this way also I can get the value of b. So if s equals 2, then the value of b is equal to 25 over 6. Okay, on the left hand side we have 25. Here we have 6 times b, so b equals 25 over 6. In similar manner, also here we have if s equals negative 4, these two things will disappear, right? Only the term which has c left, then I can get the value of c. So here we have if s equals negative 4, then c is equal to 1 over 30. So that means that this thing, right, I can decompose in this way, where this capital A equals negative 16 over 5, and B equals 25 over 6, and C equals 1 over 30. And actually, all these numbers are constant numbers. And using the linearity property of Laplace transform, I can just take them out, right? So now if I write this fraction, what we have here, this thing, right, this thing is equal to minus 16 over 5 over s minus 1 plus 25 over 6 over s minus 2 plus c, that is 1 over 30 over s plus 4. So now if I just put this expression instead of this one, and using the linearity property of inverse Laplace transform, what we get here, I can just write it as this thing is constant, right? And I can just write them separately, right, first. And after that, I can take this constant number out. So here we have minus 16 over 5, 1 over s minus 1. Plus, here we have 25 over 6. It's just a constant number. Take this out. Laplace, inverse Laplace transform of 1 over s minus 2. Plus 1 over 30. Also take this out here. And these things, we are familiar with this thing, right? If you remember, what functions Laplace transform gives us 1 over s minus 1, that is e to the power t. That is e to the power 1 times t, right? Because e to the power at, its Laplace transform is 1 over s minus a. So here it is 1. And how about this one? It is e to the power 2t, right? And that is the Laplace transform of e to the power minus 4t. So that gives us here, that is minus 16 over 5 times this thing is e to the power t, 25 over 6 times this thing is e to the power 2t, and 1 over 30 times e to the power negative 4t. Okay, so inverse of this thing, right, that is equal to this expression, or this function. That is our f of t, and that is our capital F of s. Okay, and that is how we return actually from s to t, from s to f. Okay. All right. Okay, that's it. As you see, it's quite easy, not so complicated. Now we will talk about transform of a derivative. Okay, that's also interesting thing. Here it says that in this theorem, if this f prime, f double prime, f triple prime, and these are just the orders of the derivatives, right? The zero order, first order, second order. This one is n minus 1th order derivatives are continuous on this interval and are of exponential order. And also, you know now what we mean by exponential order, right? That means that we have such positive c and m and also t where this inequality holds m times e to the power ct. That means that after some point, such point exists, right? After that point, this function, right, this f grows slowly than this function, right? Then we say that it's of exponential order. And if this nth order derivative of f is piecewise continuous on this, okay, then it is equal to this thing. Okay, that is a formula. And how we get this, we'll talk about this. That means that first, by just using the integration by parts, the first step. Okay, because here we are talking about Laplace transform of nth order derivative of f. Because yesterday we learned how to do or apply Laplace transform on a function, right? But here we are studying or we are learning how to do this Laplace transformation on the derivative of the function. Okay, and because after all we are going to solve, actually why we are learning this, to be able to solve this equation, for example the second order linear equation, a sub 2 y double prime plus a sub 1 y prime plus a sub 0 y is equal to, on the right hand side, let's say we have some function g of t, right? So now if I just take Laplace transform of both sides, what I have here, I will have here a sub 2 times Laplace transform of y double prime plus a sub 1 Laplace transform of y prime and plus a sub 0 times Laplace transform of y. I'm writing that separately because this transformation is linear, right? We're just using the linearity property of Laplace transform. On the right hand side, also we have Laplace transform of this g of t. Okay. Now, when you just do this transformation on this equation, now what I get here, we just get algebraic equation in capital F of S, because here I get something in capital F of S, I get something in capital F of S, I get something in capital F of S. And also we can evaluate Laplace transform of this function, and after that, from this equation, I can get some expression for capital F of S, and after that, applying the inverse Laplace transform, I can get the original function, this y. Okay, that is a procedure. Okay, so now how we obtain that formula? You don't have to memorize it, but actually also for memorizing it's really easy. For example, here we have Laplace transform of, all right, here we have f prime of t, the derivative of some function. Okay, how do you evaluate this? Just using the definition. We know the definition of Laplace transform, right? That is integral from 0 to positive infinity. Positive infinity. Here we have e to the power minus st times f prime of t. And here we have dt, right? So I can just bring this inside. What I get here, integral from 0 to positive infinity, e to the power minus st df of t. Okay, that is equal to, but we know how to calculate this integral, but just integration by parts. Here we have e to the power minus st times f of t. Here we have unwanted line. Okay, here we have from 0 to positive infinity, right? Minus integral. Here we have f of t d e to the power minus st, which is equal to, Now we are using the second part of the theorem, and also we are assuming that f of t is of exponential order. That means that when t is very big, okay, this function, actually this function grows slower than this function, and that's why actually when t is very big, this function is much bigger than this function. Okay, of exponential order means this. So that means that when t is big, this limit of this function f over e to the power st, that's equal to 0. Okay, that means that here we have 0 minus, how about the value of this thing at 0? Here we have e to the power 0, that's equal to 1, f of 0, so here we have f of 0 minus, how about this thing? Again, if I just bring it back here, right, I should differentiate this. So negative s comes to the front with this minus. Here we have plus. Here we have s times integral from 0 to positive infinity. Here I have e to the power minus st. Here we have f of t and dt, right? Now let me simplify this. What we get here equals, here we have minus f of s, right? Here we have s times, what is this thing? It is just Laplace transform of this function, right? And that is capital F of s. This is how we denote it, right? And here we have negative f of 0 minus f of 0. Okay, so actually it's really helpful to solve initial value problem if I know the value of the function at 0, right? And if you're given second order differential equation or first order by using Laplace transform, we can solve in this way. All right, we have 10 minutes left. How about the second order? In similar way, as you see here, this is our first outcome, right? The first result. And how about Laplace transform of f double prime? But in that equation here we have y double prime. Doesn't matter. So again, by just applying the definition to this, here we have from 0 to positive infinity, right? Here we have e to the power minus st times f double prime of t, and here we have dt, right? So if I just bring this same inside, because this thing is just the differential of f prime of t, right? So that is equal to integral from 0 to positive infinity. Here we have e to the power minus st d f prime of t, right? And again, integrating this by parts. So here we have e to the power minus st. Again, here we have unwanted straight line. All right, e to the power s negative st, and here we have f prime of t, right? And from 0 to positive infinity, right? And here we have minus, I need to interchange these two functions. So here we have integral from 0 to positive infinity. Here we have f prime of t, and here we have d e to the power minus st. Okay. All right, so continue equals, again, this function, right? That's also continuous, and continuous means, what do we mean by this? It is bounded, right? So anyway, this function is also of exponential order. When t is very big, this function grows much faster than this, so the ratio is equal to 0. So here we have 0 minus, how about the value of this function at 0? E to the power 0 is equal to 1. So here I have f prime of 0 minus, now if we just bring this inside, right? Again, this negative s comes to the front. So with this minus, it is s times integral from 0 to positive infinity e to the power st f prime of t, and here we have dt equals, now let me just write this thing first. Here we have s, and this expression we have just calculated, right? Evaluated here. E to the power minus st, e to the power minus st, f prime of t, f prime of t dt, the same thing. And that thing is equal to what? Is equal to this, right? So if I substitute here, what I have here, s times capital F of s and minus, here we have minus f of 0. And within one more term here, that is minus f prime of 0, which is equal to, let me change the marker color here. So if you just remove the brackets now, s times s, here I have s squared times capital F of s, right? And multiplies by this, minus s times f of 0, minus, here we have f prime of 0. Okay. All right. When it is 1, I got here, let's see here, s, f of s, always here we have, if it is s, we have the first order, here we have s. And here we have s squared. And if you try to find the third one, for example, Laplace transform of f triple prime, for example, what do we get here? Very similar expression, right? If you notice here, for example, here we have s to the power 0, and here we have the 0 order of derivative, right? And also here we have 2, right? Here we have 1, and here we have 2, and here we have 1. Anyway, so when it is 3, it will be like s cubed times f of s, right? And after s cubed, now here we have polar minus here, s squared, and starting with this, that is f of 0 minus s times f prime of 0 minus, because now it is 3, 2, 1, s to the power 0, that is just 1, right? How about this capital with capital F? Here we have f, here we have the order of the derivative is 0, and here it is order is 1, here we have order is 2, f double prime 0. Okay. Now, how about if we have 4? So it will start with 4, s to the power 4, and always in the first place we have capital F, and the rest is in terms of this, the powers of s, and using the initial values here. Okay, and that's why here we have in the theorem, as you see here, when it is n, s to the power n, right? Well, first we have capital N, and after that, this is decreasing. The degree of s is decreasing. N minus 1, n minus 2, blah, blah, blah. And also derivative starting from here, 0 order derivative of this function, first order, second order, third order, n minus 1's order, because it is n, right? Because if you're solving the second order differential equation, for example, to be able to solve this for the initial value problem, we must be given 2 conditions, right? Why? Because when you solve this, we'll have 2 arbitrary constants in the solution. To determine those constants, actually, we must be given 2 conditions here. That is, the first thing is, for example, the value of the function 0, that's equal to y sub 0, and the derivative of the function at the at that point, for example, y1. So if you're given these 2 conditions, then I will be able to solve this initial value problem. Okay, that's all about this. All right, gentlemen, let's have some break, okay? And we have around 3 minutes left. If I start the next question, we will not be able to finish it, okay? After 10 minutes, we will continue. Now, let's have break.